Welcome. My name is Hawk Jones, and I'll be the moderator for this Engineers Without Borders webinar, Water Supply, Part 2 of 3, Distribution. This presentation is one of the core programs in the expanding series of online, on-demand continuing education programs created by Engineers Without Borders USA and presented by Contract Solutions Group. Before I turn the program over to our presenter, I'd like to make a couple of announcements regarding the program. As our program begins, you will notice the program itself will fill the majority of your computer screen. On the lower left of your screen, you'll see a pause play button. If for any reason you need to pause the presentation, click once on the pause button. To restart the program, simply click on the play arrow that will appear in the same place. If you should need technical assistance, please click on the email link for Client Services at Contract Solutions Group, located on our website pages. Or you may call us for assistance from 7 a.m. Pacific Time until 4:30 p.m. Pacific Time, Monday through Fridays. If you are disconnected from the webinar due to local internet issues, simply log back in through the Engineers Without Borders website and restart the program. After the program, you will be taken directly to the attendance reporting page. It is very important that you complete this short form and submit it immediately upon completion of the program to receive full credit for your participation in this program. If this step is bypassed, neither you nor your chapter will receive credit. Now it's my pleasure to introduce our presenter for the program, Dr. Jeff Brown, an assistant professor of engineering at Hope College in Holland, Michigan, who joined the faculty in 2005 after receiving his Ph.D. in civil engineering from the University of Florida. Before he received his doctorate, Jeff was a Peace Corps volunteer in Tanzania, where he was a math and physics teacher in a government secondary school. Today, Dr. Brown serves as the faculty advisor of the Hope College student chapter of EWB-USA, as well as the chair for the Great Lakes Region Technical Advisory Committee of EWB-USA. Jeff, I'll turn the program over to you.
Okay, well, I guess I'm live here. Thank you all for attending this webinar, and we have probably somewhere between 60 minutes to 90 minutes of material to cover. I'll just go ahead and jump right in and maybe expand a little bit more on what the moderator started talking about, that this is really just one piece in a much larger technical webinar series. Today we're going to be talking about water supply systems that you might commonly experience in an EWB project, but there's certainly a lot of crossover and cross-linkages between this webinar and other webinars that are available to you. So webinars on structural engineering, construction, sanitation, and sustainability all tie into the material that we're covering today. So if you notice from looking at the chart there on this webinar that your project also contains other pieces, you definitely want to go ahead and check out the those other webinars that are also going to be applicable. Today, like I said, we'll be focusing on the water supply systems, and I will start with some general background about the importance of improved water supply systems and how these supply systems fit into larger development objectives, community scale water systems. We'll talk about some of the technical considerations that you'll want to keep in mind as you're really throughout the entire process, where you're beginning the process of discussing a water supply system with a community all the way through the design phase, through the construction phase, and then into the operation and maintenance phase as well. So it's really meant to be a broad overview of the water supply process. We'll also touch a little bit on project sustainability, and we've got a few really good lessons learned from other EWB projects that have already been constructed. And of course, there will also be a long list of references at the end that should provide a lot more information on some of the details that we probably won't have time to get into. We won't be covering this from the perspective of a fluid mechanics class or getting into too many of the specific design details for pipelines or water tanks. And then the other two really key components of water projects for EWB projects would be assessing or selecting a water resource and water treatment, and those are also covered in other webinars. So we're just going to be focusing on the water supply portion today. We also won't cover too much on surveying. We'll talk about it a little bit, and then there'll also be a little bit of discussion on assessment, but there's a much broader webinar on EWB project, the EWB project process, that will cover those topics. Okay, so backing up a little bit into more of the big picture discussion about why improved water supply is important, I think it's very easy for engineers to take the perspective that there's a requirement, or every person has a certain amount of water that's required, and so we're just going to design a system to supply water. If you look at it from, say, the standpoint of a public health official or somebody that's responsible for ensuring public health, you really kind of get the impression that water supply or water quantity is really one of four major areas that need to be addressed in order to recognize any type of health benefits for a community in the water supply sector. And so the other three very important topics are water quality, proper sanitation facilities, so is human excreta being disposed of properly, and then also general personal hygiene. So those other three items listed there are equally important to actually just providing the amount of water that people need. As far as water quantity goes specifically, the World Health Organization actually breaks this down into some pretty convenient categories that are very useful when you're trying to first define the scope of your project and figure out exactly what it is that you're trying to do in your community. And so if you look at the table there on the left-hand column, there are four basic service levels that the World Health Organization has identified, ranging from no access at the very top there, considered less than 5 liters per person per day, moving into basic access, where people are typically limited to around 20 liters of water per person per day, which is about the equivalent of a 5-gallon bucket. Then going to intermediate access, moving into about 50 liters per person per day, and then finally optimal access, where people have access to over 100 liters of water per person per day. So optimal access is what we would typically enjoy here in the U.S. And the range of other levels are what you might expect to find in a typical EWB project. And so it's important to remember that as far as developing the scope or deciding on the scope of a particular EWB project, that you're typically going to want to be moving from one of these service levels to the next one up. It's very unlikely that you're going to be able to design a system, construct a system, and maintain a system that brings a community from no access all the way up to optimal access in the period of time that EWB projects typically run. So, but this chart is very useful, though, in recognizing that if you hope to see some type of health gains result from your project, then you're going to have to move from one of these service levels up to a higher level. I think it's also important to understand some fundamental differences or distinctions in the types of water supply systems that you're likely to encounter in an EWB project. We've broken it up into two basic categories, one being a household scale model, where the water is typically collected from the source by the user and then distributed manually. So this is basically people carrying water from the source back to their homes. hopefully providing some type of a treatment to that water if there's contamination present, and then the users are responsible for storing the water in their own containers on site. They're also responsible for keeping the water clean and disinfected once they've retrieved it. And so this model is contrasted with the community scale model, where again the source options may be similar, either a well, a spring, surface water, or rainwater harvesting, but then in the community scale model, typically some type of treatment is provided on a large scale, either through chlorination, slow sand filtration, and then that water, once it's treated, is stored in a centralized tank and then distributed through some type of a piping system. So again, a lot of EWB projects are designed to go from the household scale model up to the community scale model, but there are also some improvements that can be made on the water supply side within each of these models, if those are what are currently in use in your community. As I mentioned before, regarding the source options, the other water resources webinar, part 1 of this 3-part series, will describe that issue. On the treatment side as well, the third webinar in the series on water treatment will discuss those different treatment options, both at the household level and community scale. And then today we'll just be focusing on some aspects of manual distribution and what can be done to improve things on that front, and then also on the community scale with centralized storage and piped distribution. Just a quick slide to maybe give you a little bit of an impression about what typical EWB water projects might look like. Again, the goal typically is not to provide direct hookups to every household in a community, but rather to make water more available to a large number of people in the community through either community tap stands, perhaps it could be the development of a well, or improvements to an existing well. So there are a lot of different ways to go about it, but this just gives you a general sense of what some of these projects look like. Focusing again then on the water supply systems for the 2 different models, both the household scale and the community scale. What we'll start with is looking at the household scale model, and well, before that we'll just do some comparisons of the 2 and talk a little bit about what some of the advantages and disadvantages are. At the household scale level, even though people are required to spend a lot of time and energy collecting their water, the benefits are that it's not a very complicated system. It doesn't require a lot of community organization, and there really aren't any maintenance costs associated with that. Some disadvantages, though, for household scale model in a lot of communities, depending on the local climate or local geology, the water might not be present throughout the year. So that can be an important issue to overcome. As far as the community scale goes, their obvious benefit is related to a reduction in the amount of time and energy that it takes to collect water. It's also possible, perhaps, to provide access to an improved source. So rather than having people collect water from a surface water stream, it may be possible to identify the source of that stream or a spring and connect a better source up to the community. And the downside, though, to all of the benefits on the community scale model typically relate to cost, and both the initial capital costs and the long-term operation and maintenance costs but also the amount of organization that's required. You really need to have everybody in the community committed to the project, dedicated to seeing it through, and also willing to contribute financially to support the project over the long run. So again, as we're considering the types of systems that are going to be implemented in particular communities, just make sure that everybody in the community is aware of the benefits and costs or considerations associated with moving from one system to another. So again, if we're dealing with the household model or household water supplies, there still are some basic improvement strategies that can be done from the water supply standpoint. On the improving access side, you can look at making new sources available to a community. So even if people are still going to be required to carry their water back to their house, if you make a new source available, such as a well or improving a spring, that can still be a positive benefit to the community. Another big issue that a lot of water supply projects can benefit from is source zone protection, and so this might deal with creating setbacks around water sources, making sure that livestock or human activity is limited in the region where people are collecting their water. On the distribution side, there are a number of things that can be done in the area of wells, so improving the pumps that are being used, providing better facilities for people to collect the water. And then on the transport side, there's some interesting transportation containers. I'll show those slides in a second. And then on the treatment side, looking at doing some type of household water treatment, providing some more unique household containers, perhaps being able to store more water on site for each household to use, perhaps for portions of the dry season. Those can all be significant improvements to that household water supply model. Again, so here are just some pictures showing improvements at the source. If you can take a spring and construct a spring box and allow people to collect water in a more sanitary way, that can be a significant improvement. Then some novel transportation ideas are shown there on the right. The hippo barrels are a good idea for those situations where you might not be able to introduce some type of a distribution system, but this is certainly an improvement over carrying 5 gallons of water at a time. Okay, and so I think most of the rest of the webinar is going to be devoted to the community scale water supply and developing those systems. Some of the same improvements to the source that I mentioned for the household system also apply here on the community scale side, but then where things really start to become different relates to the centralized storage facilities. And so again, some incremental improvements that may be part of an EWB project would be providing the appropriate size tank, perhaps to be able to accommodate the peak demand of the system, providing adding treatment to an existing water system, and also the introducing the notion of separating potable versus non-potable water supplies. And then on the distribution side, again, treatment is another thing that can be introduced at the end of that, but then also improving the location of tap stands or providing household connections, increasing security around where people are actually going to get get their water. And then on the general sanitation side, making sure that everybody in the community, if they're using containers for storage, are well versed in safe water handling practices and know what to do to keep their water clean once they collect it. I've created just a brief example, and this kind of gets into the initial, perhaps preliminary design phase when you're trying to figure out what may or may not be possible for a community-scale gravity-fed water distribution system in a particular community. And so what I've done here is just identified a very simple community-scale system that consists of a source and a storage tank, and then 3 tap stands that are going to be coming off of a distribution line. So again, just trying to highlight some of the main components and main features of these systems, and trying to also lay the groundwork for the types of information that you're going to need at a very minimum from your either assessment trip or data that you've gathered through your community partners in order to be able to design these water distribution systems. And so I've got basic information about latitude, longitude, and elevation for the source, the storage tank, and then where these different tap stands are going to be located. Just a little terminology difference here, terminology about the system. You've got the conduction line, you see on the figure on the right there, connecting the source to the storage tank. And so those conduction lines are basically designed to be flowing nonstop and basically transporting water from the source to the storage tank, and then a main line or a distribution line that sends water from the tank down to the individual tap stands. So just think about a typical design problem for the conduction line. We're going to be required to figure out what's the pipe diameter and what material do we need for this conduction line. But that, again, really requires us to know a little bit more about the system that we're designing. So if we want to start with the basic information about the population of the community, in this case we're dealing with about 300 people, and we've decided that we're going to move into that optimal access category and be prepared to provide 100 liters of water per person per day, then that means the average daily demand that we're going to need to convey from the source over to the storage tank is going to be around 30,000 liters. This gives us a minimum flow rate that we need to be able to move through the pipe of about 0.35 liters per second, or 5.5 gallons per minute. And so that's kind of the key operating parameter for this conduction line, is what's the flow rate that we need to be able to move from the source to the storage tank. But then the other important factor is the maximum static pressure that this line is going to be subjected to. In this example, we show a source that kind of, the line drops down into a valley and then goes back up onto a hill for the storage tank. And so even though the elevation difference between the source and the storage tank is about 100 feet, there's a maximum pressure there of 200 feet that this pipe material needs to be able to withstand. So again, if you want to think about this in terms of what's happening with the pressure in the pipeline, if the source is connected to the tank but the tank is closed, if you could somehow insert these little standpipes into the line, you would see that the static water level would be the same everywhere in the pipeline. And so what we want to do is make sure that when the water's flowing at our specified rate of 5.5 gallons per minute, that hydraulic grade line always pushes water in the right direction, and so that's really described by that dynamic hydraulic grade line. And so what we're trying to ensure by selecting the correct pipe diameter is that the amount of residual head or residual pressure at the storage tank, first of all, stays a positive value, and then ideally you want to maintain about 30 feet of residual pressure there at the storage tank. So now our question becomes, what size pipe diameter would be necessary in order to convey 5.5 gallons per minute over a distance of 3,960 feet on the horizontal, but then we're only going to be allowed to lose 70 feet of that total static pressure that we started with from that static hydraulic grade line. There are a lot of different ways to go about this. You can look up friction factors and solve the problem through some trial and error approaches. Perhaps the easiest way, though, is to use one of these friction or head loss tables for standard pipe diameters. And so the way that we would solve this problem for our particular system here is we would look at the column on the left and identify our flow rate of 5.5 gallons per minute. And then, again, we're allowed to lose 70 feet over 3,960 feet of horizontal pipe length. And so that turns out to be 1.77 feet of head loss per 100 feet of pipe length in the horizontal. And so the number that we're looking for then is the nominal inside pipe diameter, or the nominal pipe diameter, that gives us less than 1.77 feet of head loss at that flow of 5.5 gallons per minute. And so if you follow that 5.5 gallons per minute over and try to use a half-inch pipe, you'll see that you've got 24.9 feet of head loss per 100 feet. So that's not going to work. You have to go all the way over to the 1.5-inch diameter pipe to get below the 1.77 feet of head loss that's allowable. The other question that we had to answer, though, had to do with the pipe material that was going to be needed to essentially resist the maximum pressure that develops in the system. And again, for this example, the maximum pressure we said was 200 feet of H2O. That translates into about 87 psi. Well, of course, different pipe materials are going to have different pressure ratings, and you can see for this example here, and depending on the different pipe material, those pressure ratings actually vary depending on the pipe diameter. So there are a lot of different factors that have to come into play here, but it looks like for this example, if our maximum pressure is 87 psi, we should be fine with, for a 1.5-inch diameter pipe, we should be fine with the Schedule 40 PVC and not be required to use the Schedule 80, which has a higher pressure rating. There's some other important checks, though, that need to be made for pipeline systems such as this. The velocity of water in the pipe can become an issue if the velocity is too slow in the pipeline. So you can, of course, calculate the velocity in the pipeline by taking your flow rate and dividing it by the cross-sectional area. In this case, it turns out to be about 0.44 meters per second to move that 5.5 gallons per minute through the pipe. The actual recommended minimum allowable velocity is 0.7 meters per second, and the reason why that minimum is there is you don't want any sediment that's in the pipeline to start dropping out if the water's moving too slowly and potentially clog the pipe. You also don't want to have your water flowing so quickly. The upper limit is typically specified at around 3 meters per second, and that's in order to prevent scour along the pipeline. So in this case, we've actually specified a pipe diameter that results in a flow rate that's probably a little bit too slow. Fortunately, there are some ways to deal with that issue, providing a cleanout port along the line, typically at the point of maximum static pressure. That would allow you to open your cleanout port periodically and increase the velocity and essentially flush the system out. Another problem that's sometimes encountered in pipeline systems has to do with air blockages. Again, if you have a pipeline that has several hills and valleys in it, if you get air blocked at the top of a hill, it's good to have an air release at those locations so you can get the system flowing again. But again, for all of either the cleanout ports or the air releases, it's just important to make sure that everything is accessible, yet at the same time secured, so that way people can't get in and make any changes to the system that you're not aware of. So again, we just talked a little bit about the conduction line and designing that piece of pipe from the source over to the storage tank. I'll talk now, just provide a couple of basic considerations about that main line or the distribution line and focus on the elevation differences and static pressure issues there. Of course, if we're dealing with the main line, we're still always going to be concerned about the maximum static pressure in the pipeline. That problem doesn't go away, but one main difference, though, for the main line of the water distribution system is you need to make sure that you've also made provisions for the maximum static pressure at each of the tap stand locations. The goal, or what people typically try to shoot for in designing these systems, is to try to limit that maximum static pressure at any of your fixtures to about 40 meters, 130 feet of H2O, or 57 psi. So you can see from this example here, we've exceeded that maximum allowable pressure at the tap stands at both node 2 and node 3. So node 1 would be considered okay, but then the maximum static pressure at node 2 was 300 feet. The maximum static pressure at node 3 was 400 feet. And so the concern here is that if you have a lot of static pressure, once you open the system and water begins flowing, if you close the tap too quickly, you can develop a really big pressure spike due to the water hammer effect, and you can end up just blowing the tap right off of your tap stand. And so that's the main concern. A lot of this, it's actually more of a concern in applications here in the U.S. if you ever have any type of appliance or valve that's controlled by a solenoid where the valve is turned on and off very quickly. That can cause even more problems. So the good news is if it's just a tap where you're required to turn it on and off manually, the rate at which the tap is closed can help to alleviate some of these concerns about water pressure. But again, ideally you want to limit that maximum static pressure to around 40 meters or 130 feet of water pressure. If that's not possible, then you want to make sure that whatever accessories you're using in your system are capable of resisting that maximum water pressure. Another alternative is to install a globe valve or some type of a flow regulating valve just before that tap in order to reduce the total flow that's coming out of the out of the tap, so that way when the tap is turned off, you don't have that extreme backup of pressure in the system. And then the third option that's listed there, if you're unable to maintain the 40 meters, is to install a brake pressure tank in the system. And so that would be perhaps a very good solution for this example problem that we're looking at. Perhaps between node 1 and node 2, another small tank could be inserted to the system to essentially reset that hydraulic grade line. And so picture here on the top of what's happening in a brake pressure tank. So you've got your high pressure water coming in on the inlet side, and then a small tank and the important thing here, though, is that you've got to have a float valve to really regulate the flow of water from the high pressure side to the outlet. If you don't have a float valve there, then it would be possible for the water to just flow nonstop, and that may not be not be what you want. But anyway, the outlet water then essentially gets reset to atmospheric pressure, so this essentially reduces the overall static pressure in the system. The other option is to go with what's called a pressure reducing valve, and so these can be placed in line anywhere in the system where you have excessive static water pressure, and these actually work to reduce the static water pressure through a spring and diaphragm mechanism that you can see on the bottom left there. The only consideration for this particular strategy is that these pressure reducing valves do require additional maintenance. They can need people that are experienced with their use to install and maintain them, and they may not really even be available in your location. So depending on the sophistication of the overall system, options, a brake pressure tank may be the more appropriate option. Just a quick slide here that kind of quantifies that water hammer phenomenon that I spoke about regarding the excessive pressure buildup if you close a tap too quickly. Okay, so we'll shift gears a little bit now and again talk about some big picture considerations for that main line and trying to figure out how to size that and what are some of the considerations that you need to make. First of all, the most important consideration for that distribution line is that it needs to be designed to handle peak demands. And so this is very different from that conduction line that we looked at, where the whole purpose of the conduction line was to convey the total daily demand of water spread out over a 24-hour period. On the main line, you've got to be able to deliver larger volumes of water over a shorter period of time to meet that peak demand. And so you can imagine in the morning, everybody gets up and wants to go and get water to get things started for the day. People are going to go to the taps at the same time, open up a lot of tap stands at the same time. And so you need to make sure that you've got sufficient piping present to handle that peak demand. How you do that is a little bit of an art form, and there are some guidelines that we've listed here. The biggest consideration is if you're dealing with community taps, so this, again, with a community tap, you're expecting that multiple families are going to go to these locations and use them together, or you're dealing with a situation where you've got taps in individual households or on individual plots of land. What is the likelihood that they're all going to be on at the same time? If you're dealing with a community scale system, a good rule of thumb is to design your system such that each tap can be open and providing water at a rate of about 0.2 liters per second. The 0.1 value is a pretty low minimum to provide, especially if you're dealing with community situations where people may be waiting in line to fill up buckets so they can get back home. So about 0.2 liters per second is a good rule of thumb. And then another consideration is that storage is whether or not how your storage tank is sized in order to manage that peak demand. But again, I think the most important thing is that you're very clear with the community and have a good understanding of how the community collects their water, and then making sure that the distribution system that you design is going to meet their needs. On the modeling side, again, most of the systems that are common for EWB projects are probably going to be designed with an Excel spreadsheet, because you're typically dealing with a single line. You don't have a closed loop system. You're not trying to accommodate fire flows or anything like that. But there are, just to point out that there are some other more advanced modeling softwares out there if you do find yourself in a situation where you're dealing with multiple sources or need to do something a little bit more than an Excel spreadsheet can deliver. Okay, so mention just a little bit about data collection and surveying for these systems. For water projects, I think having accurate survey data, good topography data is really important, all the way from the conceptual design phase when you're really trying to work with the community to figure out, okay, what are the extents of the system going to be? Yes, there might be 5 families living on the top of the hill, but if the spring is at a lower elevation, then you're not going to be able to use a gravity system to provide water there. And so making sure that you have a good data set that includes elevation is really important almost from the beginning of the project. The good thing about GPS units is that they're very good for getting latitude and longitude, so it's easy to work with a community and map out the boundaries of the community, map out the location of the springs, map out where the desired tap stands might be. But then if you want good elevation data that you're going to use to actually design the system, that typically involves some type of field measurement. So using a hand level, ABNY level, or even an automatic land surveying level or a theodolite is usually going to be necessary to be able to complete the design of the water distribution system. Trenching is another very important part of these projects, and this is, I think, where the community aspect or community nature of a lot of EWB projects really get to come to the surface and shine. There a lot of issues to consider and a lot of guidelines to be aware of. I think the biggest issue or biggest factor that you'll want to develop a feel for very quickly in the project process is figuring out how easy is it to actually trench or dig a trench in this area. If you're proposing a project that's going to have a 5-kilometer pipeline, but it's all rocky ground and nobody can dig through it, then that's going to pose some serious problems. So one of the first things to do on an assessment trip is to get an idea from the community, what are the soil conditions in the area and how easy is it to dig a 1 meter deep trench, and try to get a feel for, how interested and capable is the community in getting out and getting involved in that process. Another consideration as far as trenching goes too has to do with rainy season versus dry season. In certain climates, if it's a clay soil during the dry season, the ground may be so hard that it can't hardly be broken with a pickaxe. But then if you come back 2 or 3 months later during the rainy season, it's nice and soft, and everything can get done very easily. So that's another good thing to talk with your community about as you're trying to schedule the construction of these systems, is trying to figure out where or when would be the most appropriate time to engage in these large trenching operations. So there are a few more points on the left there that you can take a look at as well. As far as pipeline materials goes, there's a lot of considerations here, and a lot of things depend on where your community is and what's available, what might be available locally. But in general, we're going to be talking about either steel pipe or some kind of plastic pipe. Steel pipe, you'll find, tends to be very expensive. You typically would only use steel pipe if you're trying to go underneath a roadway where you might be concerned about vehicle loads or traffic loads that would be potentially damaging to a plastic pipe. The other time that you'll see steel pipe used is for anytime you've got pipeline running above ground. The concern with plastic piping is that it degrades when it's confronted with any type of UV exposure, and so steel pipe is resistant to UV and would tend to be a more durable alternative if it's going to be if the pipeline is going to be exposed. So if you for whatever reason cannot get a trench dug and need to have pipeline laying on the ground, it would need to be steel pipe, and then tap stands are typically made of steel pipe as well. The challenge with steel is that making the connections are not always easy. You've got to actually cut the threads, or if you cut the pipe, then you've also got to cut your own threads, and that tends to require some relatively specialized equipment. Now, people have been using steel pipe around the world for a long time, so you're always going to be able to find somebody that can thread pipe for you, but it may not be out in the village. It may be in the regional city or provincial city where you actually bought the steel pipe. So if you're using steel pipe, make sure that you either have the tools you need to cut the threads when you arrive in your community, or that you've made all of the appropriate threadings and connections when you purchase the pipe. Again, here's some examples of exposed pipelines, and where you would definitely want to include a steel pipe and not use plastic pipe. PVC is also a very commonly available material around the world. The great benefit of PVC is that you can join the pieces together with PVC cement, so that's a pretty easy way to develop good sturdy connections. It's probably a good idea, though, when you're out doing an assessment trip, stop by the local hardware store or plumbing supply store or wherever it is that you may get your pipe, and actually take some samples and bring some samples of the different pipe diameters back to school with you, back to the U.S., and also get some sample fittings as well, and just make sure that you have a good understanding of how the locals refer to a particular pipe size, and then how you would refer to that particular pipe size in your design. There's often some confusion about the outer diameter of the pipe versus the inner diameter of the pipe, And it's very easy to either get the wrong fittings that may not work if you've specified the outer diameter and the plumber thinks you're specifying the inner diameter, or the hardware store thinks you're specifying the inner diameter. So just make sure that you have both a good idea of what's available locally and then how the locals refer to the different pipe sizes and different grades of material. In the U.S., it's common to talk about PVC in terms of either Schedule 40 or Schedule 80. I've never heard that term used in Africa. They've got a very different system for describing the various pressure ratings of their pipe there. So just make sure that you've got that you've understood all of those different details. The big constraint with PVC, like I mentioned before, was that it's sensitive to UV light. So the PVC pipe will crack if it's exposed to sunlight. The pressure rating of PVC pipe is also going to be lower than steel pipe. And again, making sure you've got the right size fittings and that all of the fittings are constructed well, high tolerance parts, will make sure that everything works in the field. Polyethylene is another commonly available piping material. This is used a lot in the U.S. for sprinkler systems. The main disadvantage of polyethylene pipe is that you have to either fuse it together, so fuse different segments together using heat, or use some type of a mechanical coupling to connect one piece to another, to connect tap stands, to make a T. It all has to be mechanical. So there is no polyethylene cement that you can use similar to PVC. But again, this type of material may be locally available, and it may cost less than PVC as well. So there may be advantages to using it, but just make sure that you've got all of your issues resolved as far as connections go. And then the pressure rating on polyethylene materials tends to be different than the PVC. They don't discuss it in terms of Schedule 40 or Schedule 80, but this PN number, which essentially refers to, so PN 10 would be polyethylene pipe that's rated for a static pressure of about 100 meters of water. So that's what those different pressure ratings come from there. Again, I think we touched on these for each of the different materials, but again, just make sure that you're familiar with the different plumbing processes and plumbing components that are available in your community, and ideally you're going to have somebody working on the project with you that's very proficient in making these connections and fitting all of these pieces together in such a way that they're going to recognize it and they're going to know how to fix it when it breaks. A few more pictures there of different plumbing fixtures for PVC, steel, and the polyethylene. The need for valves is very common in all water distribution systems. It's good to have a basic understanding of the different types of valves that are available, and also different types of valves and what they're commonly used for. I mentioned in the previous discussion on controlling maximum static pressure for the main line, if you do have a very high static pressure, you might want to put a globe valve right before the tap stand, and so you can see the picture of the globe valve on the left there. Those are really designed and used to regulate flow. So they're good for limiting the amount of flow. They allow for a lot of fine-tuning of the amount of flow that you're going to get through a tap stand. And so that's why globe valves are recommended if you're trying to reduce that dynamic pressure as it's flowing through the globe valve and then ultimately onto your tap stand. The other common type of valve is the gate valve, and those are typically intended for simple on-off control. So you want the system to flow, or you want the system to be closed. You don't tend to use a gate valve to regulate flow. It's either on or it's off. A check valve is commonly used if you're trying to allow flow in only one direction. Then the ball valve is also another good durable, a little bit more durable on-off type valve. But again, it doesn't work very well for the purpose of regulating flow. Okay, so up to now, we've covered the basic considerations for the conduction line, the main line of the distribution system, some of the different issues about pipe materials, how to get an idea of what the sizes of these things need to be. The other main component for almost all community scale water distribution systems is the storage tank. And it's very common to refer to this element simply as a storage tank, but there's a key distinction here in that you can really be talking about two very different things. The concept of the true meaning of the storage tank is a tank that's intended to provide storage over a period of time. So that could either be if you're trying to provide storage during a portion of the dry season. So perhaps in your community, all of the sources dry up during a certain time of the year, and you're going to try and store water or store a specific amount of water for a certain duration in order to allow people to continue using water throughout the dry season. So that's an example of a storage tank that would be used to regulate or to kind of minimize the effects of seasonal fluctuations in water availability. It may also be in the situation where if for some reason there's a pump in your system and electricity is sporadic, you need to store water for a few days in order to make it through that period where electricity might not be available. So just a quick example of a storage tank. If you've got 300 people using 100 liters of water per day, and you are simply trying to store water for 2 days to make it through whatever situation's causing that outage, then you're going to need a storage tank of about 60,000 liters, which is no small project or no small feat to accomplish. So the idea of a storage, again, just make sure that if it's a storage tank that you need, then that's how you're basing your decisions and using that type of information to figure out what the volume needs to be. Now the other type of tank that's probably much more common in typical community scale water systems is a peaking tank. And so this is basically a tank that's going to allow you to manage all of those peak demands that are going to occur during the day. So remember, the conduction line is moving water from the source to this peaking tank at a relatively steady rate throughout the day. But then you want to be able to through this peaking tank allow for everybody in the morning to go and turn on the taps and draw a significant portion of all of the water that's going to be used in the day during perhaps only 2 to 3 hours. And so this peaking tank essentially absorbs those spikes in demand and take some of the pressure off of that conduction line, or take some of the pressure off of a large diameter for that conduction line. So how do you size a peaking tank? And this is a question that is actually very difficult to answer if you don't know a lot about how your community uses water. So is the community oriented or set up in such a way that they're going to have a single peak demand? So if you look at the graph on the right-hand side there are three curves that kind of show how water might be used throughout the period of a day. And so the yellow line represents a single peak demand curve, and the pink line would be a 2-peak distribution, and then the blue line would be a 3-peak distribution. And so if you've got a good feeling for how your community works and what type of schedule they're typically using, then you can actually design your storage tank such that it never runs empty. And so through some pretty simple spreadsheet calculations, you can keep track on an hourly basis of how much water is being supplied to the tank through the conduction line, and then how much water is being drawn out of the tank through the distribution line. And you just want to make sure that the volume of tank that you've provided exceeds the volume of the tank that you've specified is sufficient, such that it never runs dry, probably with a little bit of a factor of safety there. If you don't have a good feeling for that, a typical rule of thumb would be to use about 30 to 40% of the average daily demand. So if your community is projected to require about 30,000 liters of water per day, then a rough estimate for a peaking tank would be 40% of that, or 12,000 liters. So again, the idea is that you're trying to accommodate everybody going to the tap stand, turning the tap on at the same time, and drawing down that peaking tank. The actual construction of the tank is also another primary consideration in all of these water distribution projects. I'm going to talk a little bit about different types of tank construction materials, going from masonry, polyethylene, ferrocement, and then also poured reinforced concrete tanks that are actually cast in place. The masonry tank is commonly used in a lot of developing communities. These tanks, though, that you really are going to be requiring some type of skilled mason or some very skilled labor in order to construct a watertight masonry tank. Again, depending on what's being used locally, that may provide a very clear answer as to what type of material you would want to use for your tank. If there are skilled masons in the area that have built water tanks, it makes a lot of sense to rely on their expertise and utilize the experience that they've gained through hopefully many, many years of doing this. And so a lot of EWB projects do rely on masonry tanks that are constructed locally by skilled masons. A few considerations and constraints are listed there. These tend to be really big construction projects. It's not really the type of project that a chapter is going to implement on their own in over a five-day implementation trip. So, and I guess the other consideration too is if you are using skilled labor, local contractors, that you have a very clear picture established with them about what the expected outcomes are, what the design specifications are, and you need to make sure that the tank is being constructed according to the way that it was designed by your chapter. Polyethylene tanks are also commonly available in developing countries. They you'll tend to find them closer to capital cities and provincial cities, and then less and less as you get further and further away from large municipal areas. The good thing about them is that they're relatively lightweight. They're easy to transport. The construction process is really limited to just preparing the foundation and making sure that you've got an adequate foundation. They can be elevated relatively easily if you're trying to put a system together for a school or for a very small localized community system or community tap stands. These tanks can be elevated. The disadvantage of these tanks is that they're very lightweight, and so if they're unfilled and the wind blows, they can move down the road. They also tend to be black in order to prevent algae from growing in them. That can have the effect of increasing water temperature that may not be desirable. The other disadvantage of these tanks, though, is that if they do crack after a period of time, they can be difficult to repair. So if a masonry tank cracks, there's a good chance that somebody's going to be able to fix it. If a polyethylene tank cracks, there may not be anything that can be done rather than replace the tank. So that's another important consideration. The ferrocement tanks, these are very interesting. A lot of EWB chapters have employed ferrocement tanks. Some people swear by them. Some people tend to be rather skeptical of them. I think the most important consideration for ferrocement tanks is that you really do need some skilled labor or somebody that knows what they're doing. There's very tight tolerances on the construction process, and if mistakes are made at any point along the process, it's very easy to get cracks and leaking. So again, it's one of those things where if there are ferrocement tanks that have already been constructed in the vicinity of your community, and you've got skilled labor there that knows how to build a ferrocement tank, they are advantageous from a material use standpoint. They're essentially constructed with an iron rebar cage and then some chicken wire as a mesh, and then the cement part is just kind of is plastered on, so it's not actually like a poured concrete wall. And so the amount of materials that go into these tanks tends to be much less than your typical masonry tank or reinforced concrete tank. But again, if mistakes are made, they can crack and leak, and if you don't have somebody that knows how to repair them, you can be fighting and struggling with that for a long time. There are quite a few resources out there for designing these ferrocement tanks, so you can take a look at that. The other consideration too with these is, since they don't tend to be very thick, making sure that you've got adequate provisions for live loads on the roof. You don't want somebody to be walking on top of this thing and falling through because the live loads on the roof aren't considered, so that's important. Then finally, the poured reinforced concrete. Again, there's a lot of skilled labor out there that's capable of doing this, but it does tend to be a rather large project. The major concerns can be related to cracking, leaking of the tank, making sure that the quality of the concrete that's mixed and poured for the tank walls is appropriate for a structural mix as opposed to just a slab mix or sidewalk mix or something like that. The other really important thing to point out here is that a lot of chapters tried to use ACI 318 as a concrete code in order to come up with design provisions for these tanks. It's actually ACI 350, which is a separate code for environmental structures, or basically water tanks, that you need to pay attention to. So make sure that if you are specifying a poured reinforced concrete tank, that you've made sure that all of the requirements for ACI 350 are met, not just the requirements for 318. A little bit of discussion here on preparing the foundation for a tank, making sure that the tank is located in an appropriate location. You don't want to necessarily put these things on the side of a hill where they may be subject to landslides or any type of stability issues. Other issues, if you're encountering any type of clay soil, making sure that you provided an adequate base for the tank, and also making sure that you've made provisions for any erosion issues that might occur. So if you do either overflow coming out of the tank or stormwater runoff that may be moving through the area, just making sure that you're not that's not going to undermine the foundation or cause any other problems. The tanks typically do require some kind of leak-proofing or lining. There are a few different ways of going about that, but again, I think relying on the knowledge of local contractors, local masons who have built water tanks before, they're typically going to know what is available in your area and what has been used successfully in the area that you're working. So, but again, just make sure that any coatings that do go inside of the tank are actually approved for potable water applications. Don't just settle for the paint can that somebody recommends at the hardware store. Make sure that it is in fact a product that can be used for sealing water tanks. A few additional considerations about tank designs. I mentioned for the polyethylene tanks, making sure that, or one of the drawbacks with them is that they are lightweight, and if under heavy winds, if they're empty, they can get blown away. So make sure that you have some provision for securing them in the event of high winds. The live loads on the roof, I mentioned that, especially for the ferrocement tanks. Security is also an issue, making sure that access to the tank is controlled either by some type of a locking mechanism. Providing adequate overflow can be important as well, making sure that if you do have a float valve on the tank and that float valve fails, then what are the provisions for handling any overflow that might occur, making sure that that overflow doesn't lead to the erosion problems. Here are just a few more pictures of the type of detailed drawings that you would typically want to include with your submittal for a tank. And again, I think it's good to err on the side of simplicity when you're putting these drawings together, and making sure that you can take these drawings and then communicate them with either your contractor, your mason, or the local skilled labor force that you're going to be working with to get this construction. So again, this diagram here just shows the basic dimensions of the tank, so it's good to have this so you can talk about what types of formwork might be necessary and figure out with your contractor who's going to, how much material do you need to bring, how much rock, how much sand, how much cement. And then from there, moving into reinforcement plans. So again, being very clear and very specific about how much reinforcement needs to go into these foundations, before they're actually poured, either the foundation or the walls or the roof. Here's another drawing that just shows the final reinforcing details of the tank. So again, I think it's important to have almost a series of drawings that you can use to guide the process through different phases of construction, and not just have one drawing that's very cluttered and perhaps difficult to read if you're not already skilled at picking out details from design drawings. Tap stands are another important feature of the systems. One of the main concerns or main things you want to think about when you're positioning your tap stands or locating the tap stands is making sure that you can handle any excess runoff or extra water that might be present if somebody's bucket overflows or if somebody walks away and leaves the tap open, making sure that you can handle that and it runs off without creating any other puddles or other health hazards due to the standing water. So again, I think there's some more information on that in the sanitation webinar as well. The other issue to consider for these systems at the tap stand location is, are you going to try to include any type of a metering device, and are the tap stands going to be secure? Are they going to be open for use 24 hours a day, or are they going to be, or is the access going to be limited to specific times? So those are all things that need to be discussed with the community before you actually start building them, and just making sure that everybody's on the same page. And there's a good chance that people in your community know what a tap stand should look like, have a good feeling for what tap stands are appropriate in their area, and can really be a big part of designing and implementing these as well. The operation and maintenance is another very critical component. I would venture to say that it's probably the most critical component of any type of community scale water distribution system. Regardless of the type of system, whether you're using a solar pump or a gravity-fed system, there is going to be some level of maintenance that's required. And so having an idea of what those requirements are going to be, and making sure that the community is on board with that and aware that somebody's going to have to replace valves, somebody's going to have to perhaps clean water tanks, somebody's going to have to just do general maintenance and upkeep on the system before the system gets built is very important. The idea of a fee may be something that requires some discussion before the system gets built. Depending on the community, the idea of paying for water might not be acceptable. It might take quite a bit of education before everybody's willing to contribute, again, on this community scale towards the long-term operation and maintenance of the system. The typical mechanism for doing this is some type of a community water board or water committee. And so getting one of those formed, or having one of those formed from the very beginning, really is critical, and working with them through the entire process and making sure that they're involved in decision making is critical as well. And then finally, education is a key component to making sure that these systems work. So again, the idea is never to design a system, go into a community, build the system, and then walk away. It's to make sure that everybody in the community is, or at least key people in the community, are familiar with how things were put together, what the basic requirements are for maintaining them, and then also have the leverage to extract or exact some fees for using the system. This is a big question, sustainability. There are a lot of water projects around the world that currently do not function, or they're not functioning the way that they were intended. And so ask yourself the question, if your chapter completes this project and hands over everything, over all of the operation and maintenance tasks to the water committee, what is it going to look like in 10 years? Some of the key things to consider throughout the whole process that will really ensure that the likelihood for a sustainable project is greater would be, again, focusing on locally available materials, making sure that all of the plumbing fixtures, all of the different pieces and parts can be purchased locally. So you don't want to pack your suitcase full of specialized plumbing fixtures and bring down just enough for your project, and then the first time one of them fails, nobody knows what to do with it, and suddenly the system isn't used anymore. And so I think that can also, under that same theme, is community ownership. And if you're making sure that the community is involved in the decision making about where the system is going to function in the community, but then also how you're going to achieve these goals, and what materials are going to go into it, I think that can contribute a lot. The affordability of operation and maintenance, obviously you're trying to keep that as low as possible, but again, you have to kind of balance the available resources in the community with the needs of the system. And then finally, down there at the bottom, develop some type of a plan for long-term monitoring with your system. So again, it's never about finishing the project and leaving. It's about finishing the project and then continuing to develop the skills and develop the capacity of the community to continue maintaining and operating the system. Few lessons learned. The assessment trip is obviously a very important part to the water distribution system process. And again, depending on your chapter's experience with water distribution systems, the community's experience with the water distribution systems, it's very likely that multiple assessment trips would be required. It's hard for me to imagine a chapter going on a 5-day assessment trip and collecting some data, coming back to the U.S., designing a system, and then returning for an implementation trip and completing the system in one shot. It's much more likely that you're going to go and collect some baseline data, return and do some preliminary design, and perhaps come up with several different design options for the community, go back to the community, work with the community to figure out which of these options is going to work best for them, how is it going to fit for the as far as the long-term operation and maintenance goes, and then you're going to devote your time to a complete design, developing a complete design and getting complete approval for the project, and then going through the implementation steps. So it's definitely not a assess, design, implement type process. It often requires more back and forth with the community through multiple assessment trips. The other thing that's very important, and if you're involved with a water distribution project with EWB, is going to be developing this memorandum of understanding with the community. And so again, that's just an idea of getting everything out on paper, out in the open at the very beginning with the community, to make sure that they understand what's expected of them, you understand what they're expecting of you, and making sure that those two groups are working on the same page, and everybody knows what the other person's responsible for. There are a few more things there. I think I've touched on all of those throughout the at some point or another throughout the whole webinar. But again, this whole idea of a working water board, a working water committee, as being critical for any community-based system. A few other examples here as far as lessons learned goes. Again, the issue with the ferrocement tanks, team got down to Nigeria, started construction on a tank, left the project for the local masons to finish. They didn't quite follow all of the proper procedures, and suddenly cracks were opening up, and it turned out to not work well at all. And so again, including a realistic construction schedule. What can your chapter realistically expect to accomplish? And if you are going to rely on skilled masons or skilled contractors to complete any work that's left undone, making sure that what you've specified is in line with their talents and their capabilities. The second one down there, from a case example from Nicaragua, this one's really disgusting. This one always scares the daylights out of me too. But somebody opened up the tank and threw some rats in. Maybe they were dead, maybe they were alive. Threw some rats into the tank. Nobody figured it out for a few months until the EWB chapter comes back, and you can imagine the stinky mess. So again, making sure that you've got some provision for general security is going to be really important. A lot of times, if you're working with one particular community, neighboring communities may not be thrilled by your presence. There may be some inter-community conflicts where one community may try to sabotage the system, do things to the system to prevent it from functioning properly. And so making sure that you've thought through all of those, and again, having discussions with the community before things get built is always better, because you always have a chance to plan for things through that process. The last one there, just again talking about infrastructure systems in general and the importance of operation and maintenance. And a lot of EWB projects involve some type of repair to an existing system. And so as important as doing a good job of repairing that system is also making sure that you've identified whatever it was in the process that caused the original system to break down or not function properly in the first place. So there's always going to be some type of money required to maintain these systems. And if you don't have some type of a fee structure developed and in place with the community, it's unlikely that these systems are going to operate very long into the future. Should be getting close to the end here, but these are just some key points that EWB has put together throughout their experience working with projects all over the world. But again, I think having a strong, engaged local NGO is critical to for these types of systems to function. Making sure that the NGO is aware of what it is you're doing, and that they're really acting to coordinate your efforts with the local community. That really goes a long way. Again, having that memorandum of understanding is important. The issue of land rights, and making sure that if you're proposing to put a pipeline through a particular part of the community, that whoever may own that land is agreeable to that and is willing to allow that to happen. That's important. The next one there, solid lines of communication between the project team and the community. It's very, like I mentioned before, it's very hard to collect every single bit of data that you're going to need to design a system and get it approved by TAC, and so there's always a need for more information. There's always a need for feedback from the community during the design process. You might run into a problem and realize that you can't, for some reason now, you can't fit 15 taps on your distribution line. You can only put 10 taps on the distribution line. Well, it's good to be able to air those ideas with the community and make sure that you've got their support for those changes before you go off and redesign the system and then show up and build something that nobody wants anymore. The other comments there about locally sourced materials and engaging locals during the implementation phase, that's always critical. And also making sure that your own project team has some construction experience. If you're going to be working with professionals, either contractors or skilled laborers, making sure that you know your way around a job site and you can drive a nail and do some other basic tool handling, I think that goes a long way in building relationships and keeping everybody on the same page. And then the last point there is making sure that you, particularly for water projects, making sure that you have access to the mentors and experience that you need with all these different relevant disciplines. The big challenge with these water projects is that they're really multidisciplinary engineering projects. You need to know a lot about water flow and pipes, but structural engineers typically don't know anything about water flow in pipes, or at least don't know it to the level that they may need for a particular problem. And then geotech also comes into play. And then on the public health side as well, making sure that what you're proposing to do is actually going to have some realizable benefits for the community. So I mentioned at the beginning, here's a list of references and resources. A few of these that I would point out are, of course, the EWB guidelines for water quality and water resources. The other one here is the Handbook of Gravity Flow Water Systems by Thomas Jordan. This one goes back to probably the late 60s, early 70s, but it's still a very, very valuable reference book for people designing these water distribution systems in developing countries. And so now I would again encourage everybody to keep going through the seminar series. We've got the part 3 of the 3-part series for water systems also available. That's going to cover topics related to water treatment. Again, very important to make sure that the water that people have access to, or the water that you've provided to the community, is of a suitable quality. So that webinar is going to cover both individual point-of-use water treatment technologies as well as community-scale treatment technology. So I encourage you to check that one out as well. And thank you for listening to this webinar. And more importantly, thanks for all that you do for Engineers Without Borders and the communities that you work in. So that should be it, and I will now turn it over to the moderator.
Thank you very much, Jeff, and thanks to our participants for your attention. I would like to take this opportunity to once again remind our participants that you must complete and submit your attendance on the following webpage to receive credit for attending this program. This concludes today's program, Water Supply, Part 2 of 3, Distribution, brought to you by Engineers Without Borders, USA, and Contract Solutions Group. Please check our online catalog for the latest instructional programming from EWB-USA and Contract Solutions Group. This program is copyright 2010 by EWB-USA, all rights reserved. Thank you for joining us for this program, and enjoy the rest of your day.